Okay, so we're here with week 10 material. So we're going to be talking about the Hoare chapter. In particular, we're going to look at a particular kind of logic for proving properties of programs called Hoare logic or Floyd-Hoare logic, which has been very influential since the 60s. Still relied on by a lot of proof tools and verification methods and so on. So we're going to see how to formalize that and use it to prove properties of IMP programs. So as a sort of outline in this first part of the chapter, the stuff we've got so far with IMP is we've got an ability to define what programs look like in terms of abstract syntax trees. We know how to do evaluation in terms of a relation, a partial function on states, and we are effectively in that sense defining what is often called the operational semantics of programs. In other words, what it means to run a program. And it's a very small language, but it's got some typical features of real languages that can be extended out into dealing with full-blown languages. And we've also looked at properties of the language, which is often called meta-theoretic properties. So they're not so much properties of programs, they're properties of languages in general. So we've got things like determinism evaluation, which means programs always do the same thing when you run them. Functional versus relational definition, so that's the computational versus relational version, which we can do for some kinds of programs like expressions that are not ever going to fail. We can prove things like certain programs will always terminate, or transformations of programs actually have the property that they don't change the meaning of the programs. And in the equiv chapter, most recently, we've looked at how to sort of compare two programs to each other in that sense as well. So these are all really good, and we can use them to sort of reason about particular programs as well. But the aim now is to sort of say, well, if we've got a particular program, can we verify that it does what we think it does? In other words, can we use the semantics of the programming language to reason about what a program will do when run under certain circumstances? So we're going to look at Hoare logic, which is a particular way to do this in a precise way. And basically, the high-level view is that you're sort of looking at if some assertion, some property holds before you execute some piece of code, then what do you know holds after that piece of code is executed? And if you do that for a whole program, then the thing at the end is really the guarantee that you have of what happens when you run the program. So we're going to look at Hoare logic in this chapter. Basically, you can use it to write down specifications of programs, in other words, what you think should happen under what conditions. And the proof rules that we'll look at basically let you reason about programs with respect to those specifications in a formal, structured way. And they talk about being compositional here. In other words, we don't have to reason about the whole program in one go. We can reason about different pieces of the program and connect that reasoning all together to get a property for the whole program. So let's get started. The first part is we need some notion of assertion. So essentially, you may have come across assertions in programming languages like C or Java and so on, where you can put in your code an assertion that's essentially a Boolean expression, which you're saying at that point in the code, this expression will be true. So you can sort of use it as a way of trapping. If you get to that point in the code and it's not true, then the program will terminate it with a message saying that this assertion has failed. So that's a dynamic check, right? It's only happening at runtime. So here we're doing sort of equivalent sort of thing, but we're talking about static analysis of programs, so we're analyzing them without running them necessarily. And an assertion is really just a property that holds given the state of the program. So states are what we've seen before in the previous chapters, where we can map variables to their values. So an assertion is really just a way of saying that there's some property about the state that holds. So you can see some examples here. So for example, this one is saying that in this assertion is that in the state the value of x is 3. So it covers any state where the x is 3, regardless of what all the other variable values are. The next one, for example, covers any state that the value of x is less than or equal to the value of y, and so on and so forth. Okay. Some special examples would be this one, which says that this assertion holds in any state whatsoever, and the last one, which says this is not going to hold in any state, because there's just no way to construct a false value in this logic. Okay, so we'll see some uses of this kind of assertion as we go along. Now in the comments here, they sort of suggest that it's easier to understand. If you think about it, this fun ST part is always there, right? Because the assertion is really a property of a state. So you have to have the state as an argument. And every time you use a variable, you have to apply the state to the variable to get its value, which is a bit notationally heavy. So they'll often write this sort of thing where they leave out the state part. But the implication is that this is saying in the state that we're talking about, these are the values of the variables that are in that state, not some other state. And there's only one ever state that we're talking about here, is the state that's governed by the assertion. Okay, so we can formalize this idea. So we've got assertions. We can also now talk about one assertion implying another assertion, which is going to be important for reasoning about the execution of program as it moves through the execution. So here we've got two assertions, P and Q, and we're saying that for every state, if P holds in that state, then Q holds in that state, right? So it's a logical implication, but it's quantified across every possible state that P holds in, okay? And they use this arrow, double-headed arrow notation to stand for assert implies, okay? And just like with normal implies, we can do an if and only if version, which is the double-headed version that goes both directions. So P, the assertion P implies Q and Q implies P. So we'll see that in a few places as well. Okay, so if we've got assertions, then what are we going to do with them? Well, the sort of fundamental concept for Hoare logic is the idea of a triple, which is essentially encoding this statement in the text here. So basically what we're interested in is some command. So normally Hoare triples apply to statements in an imp-like language in their sort of simplest form. So we're saying we're interested in what command C is going to do. And we're basically interested in saying, well, if we start in a state that satisfies the assertion P, and then we run C, then C will terminate in some final state that satisfies the assertion Q. So it's a triple because there's a command and two assertions. So it's a three-headed relation, if you like. And in the formal notation for our purposes, it's defined by this Hoare triple thing. So it's got P, C, and Q, and it's defined in this way. So you remember from previous chapters, this is the evaluation relation for commands that says if we run C starting in ST, we get into ST prime, right? And that's quantified across all such possibilities. Then it must be the case that if P holds in ST, then Q holds in ST prime. So this is just using the evaluation relation we saw before, combining it with the idea of assertions. Now in standard Hoare logic literature, we write triples like this with the curly braces. So we basically put this command in the middle. We put P first and Q afterwards. Sometimes P is called the precondition, Q is called the postcondition, and you put them in braces to indicate that they're not part of the program, they're just meta information, if you like, about the program. In some early programming languages, these braces were comment symbols, so this is sort of like sticking comments in your code to indicate the assertions that hold at each point. In this book, you can't use the single braces because they already mean something else, so they use this double brace notation, which is what they're defining down here. So we can have a look at a few examples of these things. So I'll skip over this one. You can have a look at that on your own, but I'll go down to this exercise here. So if you look at some of these triples, the exercise is to try and determine which ones are valid, in other words, which ones actually hold. So the first one says if you start in any state whatsoever, in other words, true holds in it, which true holds in every state, and you do an assignment of x to 5, then afterwards x is 5. Okay, that seems pretty simple. If you start in a state where x is 2 and you add 1 to x, then you end up in a state where x is 3. Okay, now remember, these assertions are covering every state where this property holds. So there are there's an infinite number of states essentially here, but all we know about it is that in those states, it's the states that only have x is true. There's 2. And you can chain the commands together, obviously. So if you have a sequence like this, you can say, well, true, I should actually be turning off my notifications, sorry about that. If we're in any state whatsoever and we do x is 5 and y is 0, then we end up in a state where x is 5. Now obviously we could have had more in this final assertion, like we also know that y is 0. But in this case, for some reason, we just want to know something about x, and the fact that y is 0 is not relevant for, say, the next part of the proof or whatever. So this one is a little trickier because if you think about this precondition, x equals 2 and x equals 3, that can never hold in any state, right? Because x can't have 2 different values. So is this triple valid or not? And if you think about the way the definition works, the definition says that in every state where this can run and terminates in another state, then the postcondition holds. But basically there are no states where this can hold, right? So we need the precondition to hold as well. And there are no such states. So this is sort of trivially valid because it's the precondition never holds. Okay? And you can see the same down here is that if the precondition is false, then it's sort of trivially valid. Okay. What about the skip one here? So skip doesn't do anything. So if we start in any state whatsoever, can we get to a state where false holds? Now we can't ever have a state where false holds because false never is true. So this is not a valid triple, right? Because there are states that match the precondition. We can run the postcondition and end up in exactly the same state as we started in, but false will not hold in that state because it doesn't hold in any state. This is our sort of standard infinite loop. Okay, so if we start in any state and we execute the infinite loop, can we get to false? Well, basically this is saying again, there are no terminating, well, in this case, there are lots of states that satisfy the precondition, basically everything, but there are no states that that this terminates in, right? So in the definition of the thing, we have to have an ST prime that is a terminating state for starting in ST and running C. And there are no such states, okay? So this is fine because this is essentially saying we can never get to this postcondition. And this is often used in program verification, not with infinite loop, but if you have a false at the end, you're basically saying, can we prove that we'll never get to the end? And that might be important for verification. What about this while loop? So if we start this while loop, we're in a state where x is 0, then we're going to increment x by 1 the first time round, and then the loop will terminate, so we'll definitely end up in a state where x equals 1. Okay. However, this one is not so good. So if we start in a state where x is 1 and we keep going while x is not 0, we'll just keep incrementing this over and over again. And can we end up in a state where x equals 100? Well, if you think about the loop, this never terminates, assuming arbitrary precision numbers, so we're never going to get to any final state. So this is sort of trivially valid as well. This might as well be false. Okay, so hopefully that gives you a sort of an informal sort of understanding of what the pre and post conditions are really doing. Okay, so we can formalize this this sort of stuff. So we'll use the whole triples a lot in what's going on, but in the first case, they're basically giving you a couple of simple theorems that sort of formalize some of the notions that we're using there. So, for example, if you know that the post condition always holds, right, in every state, then it doesn't matter what the precondition is or what the command is, you always have Q afterwards. Okay, so for example, if Q is true, just the assertion true, then obviously this is going to be trivially true, but it could be, you know, x equals x or something like that. So there's a simple proof of that, just unfolding things and using this lemma. And similarly, if you start in a state P where P doesn't hold, right? In other words, there are no states where P holds. That's what I should say. Then this is trivially true for any Q as well, because there are no states where you can start with P holding. Hence, there's no states where you can start with P holding and end up in something else after you run C. So this is sort of vacuously true, and that's what the proof will show. Okay, so that's a sort of quick introduction to assertions and Hoare triples. We'll pick up in the next part with the idea of proof rules that we use to help us verify programs.